Let's find the least squares approximating line for the following set of 4 points. Well, this least squares approximating line, it's sometimes called the least squares regression line. It's going to have a formula that looks like this. Y will be equal to some constant plus some coefficient times x. Now what we'd like to do is write this in the form of a system that we can solve. And in thinking about this system, it's important to remember that the unknowns here are actually this constant and this coefficient. So it's a0 and a1 that we're ultimately trying to find. And those are playing the role that x normally plays when we're solving a system. So in thinking about how to set up the system then, let's look at this equation here and see if we can rewrite it a little bit differently. Looking at the right side, we could write it as 1 times a0 plus x times a1, and we could say that's equal to y. So that will give us a little prompt here in terms of how to write out this system. If our a0 and a1 are over here, then we're going to need 1 to multiply with the a0, x to multiply with the a1. So that tells us how to fill in these columns here. And we want that to be equal to y over on the right side. All right, so the first column here on the left side is just going to represent a column of ones. And beside that, we're going to fill in our different x values that were given in our set of points in the problem. So the x values were 1, 2, 5, 6. All right, and then over on the right side, we're going to fill in our y values from the given set of points. So that would be 3, 4, 5, 10. Now this system, as we've written it, may not have a solution. In general, any system ax equal b may not have a solution. But if we multiply both sides of this equation by A transpose, and we get A transpose AX equals A transpose B, then this will have a solution. Let's say it has a solution, but there are a couple of comments I want to make here. So first of all, in writing this, it really would be a good idea to rename our x rather than just call it x as we did before. Let's give it a special name like x star. Because it's not necessarily the same x as we wrote in the previous line. Remember, the solution, the system ax equal b may not even have a solution. X star here represents what's called this least squares solution to the modified system. And then just a technical condition here, this modified system will have a solution when the columns of A are linearly independent. So this gives us a hint as to how to find our least squares solution x star. If we could multiply both sides by the inverse of A transpose A, then we would have isolated x star. So let's write x star is equal to A transpose A inverse times A transpose B, and that gives us the formula that we're going to get started with. From the previous screen, I've just recopied the system that we set up at the beginning of the problem, and I've recopied our formula for the least squares solution x star. So let's work towards finding x star. First thing I would probably do is work out what A transpose A looks like. A just refers to this coefficient matrix up here in our system. So if we transpose that, we get 1s along the top row, and then 1, 2, 5, 6 along the bottom row, and that's going to get multiplied by the original matrix A. So doing that matrix multiplication, we end up with a 2 by 2 matrix, which looks like 4, 14, 14, 66. Now we can find the inverse of this matrix using the formula for 2 by 2 inverse. We are going to swap the entries on the diagonal, change the sign of the off-diagonal entries, and we'll divide by the determinant of that original matrix, which is 68. So there we have the formula for our inverse. Now let's go back to our formula for x star and we'll start putting all the pieces together. We'll have to take this inverse that we've just found, multiply it by A transpose, and then by B, which in this problem is the vector which contains our constants over on the right side. All right, so this is going to look like 1 over 68 times this little 2 by 2 matrix times A transpose times the matrix B, which is the one that records our y values. And we can think about multiplying this out. Now, in terms of efficiency, it probably makes sense to multiply these guys together first. It's just going to turn into a shorter calculation that way, or smaller matrices to write down. So it might save a little bit of time from that perspective. If we multiply through, we are going to get the matrix 22, 96. And I think I'll leave this 1 over 68 out in front for now and just do this last multiplication here. We're going to get 108 and 76. Now if we look at our coefficients here, 108, 76, as well as 68, those are all divisible by 4. So we may want to actually simplify these fractions a little bit. Instead of writing 108 over 68, we might want to write 27 over 17 and 19 over 17 for the second coefficient here. Okay, now going back to our original system, remember these represented the values of A0 and A1. And our line had the form y equals A0 plus A1x. So meaning the line that we're looking for is y equals 27 over 17 plus 19 over 17 times x. That is our least squares approximating line for those 4 given points.